So this video lecture, we are going to label an electrochemical cell, or at least a diagram of an electrochemical cell. This is problem number 6 in problem set 12.2. The directions say, given the following nickel-barium voltaic cell diagram, label the anode, the cathode, positive electrode, negative electrode, the direction of electron flow, the direction of anion flow, the salt bridge, and the load. Base your decisions on reference table J. Reference table J helps us determine whether nickel or barium is going to be oxidized. And since you see that barium is higher on table J than nickel, we know that barium will undergo oxidation and nickel will undergo reduction. So what we need to do is label this diagram below. Well, first of all, taking a closer look at this, we have the barium electrode here in a solution of barium ions. We have the nickel electrode here in a solution of nickel ions. The sulfate is the spectator ion and will not do anything other than just live in the solution. Since we know the barium is going to be what gets oxidized, and the nickel is who is going to get reduced, right away we can decide which of these two electrodes is going to be the anode and which of these two electrodes is going to be the cathode. Well, there's a funny little way, a mnemonic trick that can help you do this, and this is an ox, red cat. So the site of oxidation is then labeled as the anode, and the site of reduction is what we call the cathode. All right, so let's think about what's happening. The barium, what's happening to the barium is that it is oxidizing. So if we scroll down the page a little bit to see what's happening in the later part of this problem set, we can write the oxidation half-reaction as the following. We're starting at Ba0, and it's turning into Ba plus 2 electrons. The reduction half is we are going from Ni plus 2, gaining 2 electrons, turning into Ni0. Now you might be wondering where I got the charges of the barium ion and the nickel ion from, and that's from this formula barium sulfate. It is a positive 2 in this ionic compound, and nickel also is a positive 2. So that's where the positive 2s are coming from in those. All right, so let's answer some questions about this. First of all, the oxidizing agent is the one that is getting reduced, so that is the Ni plus 2. The reducing agent is whoever is getting oxidized, that is Ba0. Determining the voltage, we have to consult over here. We have to go over to our reduction potential diagram. This is AE reference table D. We start by looking up the reduction half reaction because AE reference table D is all reduction reactions the way they are written. So if you find the Ni plus 2 turning into nickel 0, I believe that is right here. So our voltage right there is a negative 0.26 volts. Now we have to find the barium oxidation reaction, so we have to look at it in the reverse. We're looking for barium plus 2 turning into barium 0, and it is towards the bottom of the reference table. It is right here. Because this is written as reduction, but we really want to see it as oxidation, we just have to flip the sign. So instead of negative 2.91, this becomes positive 2.91. The total voltage, we just add those two numbers together. And so this works out to a positive 2.65 volts. So positive voltage means this will indeed be spontaneous. We will indeed get an electric current from this. All right, so going back up to our diagram. Okay, what else do we need to label? This is what is called the load. In this case, it is the voltmeter, but this could be the electronic device that you're powering with the battery. All right, let's go back to our site of oxidation. Barium is the anode. The barium 0 right here is losing electrons. Where are those electrons going? Well, they're being pushed out through this wire. When barium loses those electrons, what's left? Well, what's left is barium ions. Those barium ions dissolve into solution. Okay? So those electrons, let's follow the path of the electrons. They're going through the load, through the wire, towards the site of reduction, the nickel electrode. All right? And what happens here is as those electrons kind of pile up on this nickel metal strip, what happens is those negative electrons attract these nickel plus 2 ions. And so the nickel plus 2 ions turn into nickel 0 atoms. So that's what's happening there. That's the site of reduction. Other things we need to label is the positive electrode and the negative electrode. The negative electrode is always going to be the anode, right? So think of it this way. We're going to label this as the negative terminal of the battery. And so if this is the negative terminal, it's like think of it as if it is repelling electrons. And so the electrons are being forced out through that wire, right? And so why are the electrons coming over here? Well, because it is the positive electrode, and you can think of it as if the positive electrode is attracting those electrons. All right, let's see, what else do we need to label? We need to label the flow of the salt in the salt bridge. This is what we call the salt bridge. This is what completes the circuit. And what will happen is, because this solution here is getting more and more positive, if we use the sodium chloride salt bridge like we did in class, right, if this solution is becoming more and more positive, then the anions, in this case the chloride ions, will migrate here to kind of counterbalance those positive ions. And since this solution over here with the nickel is losing those positive ions, this solution over here is getting more and more negative. So the positive, the cations, will flow in this direction to counter effect that loss of positive charges. So the cations will migrate. In this case, it would be the sodium ions would migrate in that direction. So the salt bridge, you can just think about it, it's the ion flow to kind of balance the charge. Let's take a look at the questions remaining at the bottom of this page. Question F says, which of the following statements is true? The nickel electrode is getting larger because the nickel atoms are being oxidized to form nickel ions. Well, that is not correct because the nickel atoms are not being oxidized. All right. We do know that the nickel electrode is getting larger, and in this case they're getting larger because the nickel ions are being reduced to form nickel atoms. So that choice number 2 is the correct answer. Why is 3 wrong? Why is 4 wrong? The nickel, we know that the nickel electrode is not what's being oxidized, so we can eliminate that. We do know it's being reduced. But when it's being reduced, it's because sorry, not sodium, the nickel ions.
Please report to room 127. Thank you.
Nickel ions are turning to nickel atoms, and so by that fact right there, that's why the nickel electrode is getting larger. So the electrode is getting heavier. The electrode gets heavier. Right. So, all right, number 9, which of the following statements are true? What's happening at the barium electrode? We know the barium electrode is being oxidized, so we can eliminate those reduced choices. So when an electrode gets oxidized, what's happening to the actual metal electrode? Well, if it's being oxidized, it's actually dissolving into the water. So if the metal is dissolving, it's actually getting smaller. And that's because the atoms are being oxidized to form barium ions. So the correct choice there is choice 3. In what directions are the cations going across the salt bridge? Well, what we saw in that diagram up above is that they are going to the left in this case. They are going towards the nickel half cell, or the nickel side. They're going towards the nickel side. Okay. Can barium nitrate be used to make the salt bridge? Why or why not? No, it cannot be used to make the salt bridge because it is involved, it is one of the electrodes. All right, so that's why the salt in the salt bridge has to be made of a metal that is not one of the electrodes. All right, we're going to take a look at the next problem that is, okay, where I can't control it. Come on, stop. There we go. All right, so this next question, you are to design two wet voltaic cells, two wet electrochemical cells. The first cell should have the maximum possible voltage allowed for using the solid electrodes.
Tay Wu, please report to room 127.
Tay Wu is in trouble. All righty, we want the maximum possible voltage allowed using from AE table D or from table J. All right, so what we are going to do is from table J, the two most extreme metals, as you probably have guessed, are lithium and gold. And so who's the more active metal? That would be lithium 0. All right, and the less active metal is going to be gold 0. So those are the two electrodes that we are going to use. The solution that we are going to use, the best one to use is probably the nitrate solution. The nitrate's always going to be a spectator ion. It's also always soluble. So we're going to use, since nitrate is a -1 ion, right? The formula for lithium nitrate is just going to be LiNO3. Now for gold, gold can either be a +1 or it can be a +3. Right? So which one should we use? You might think we should use the +1, but we're not going to use the +1 ion because gold +1 is not included in AE reference table D, only the gold that is a +3. So because we don't have information about the gold +1, we're going to use that ion when we make our solution of gold nitrate. So AU +3 and NO3 -1 should give us that solution of AU NO3 3. Okay. So what would be the balanced reaction for the cell? Well, let's do the oxidation and reduction halves before we do the balanced reaction. So the oxidation half is going to be the lithium. Lithium 0 is going to turn into lithium +1, +1 electron. The reduction is going to be AU +3 electrons turning into AU 0. Okay, now to balance it, we're going to have to distribute a 3 through all the lithiums. So if we were to write this as a balanced equation, we would have to say 3 Li's plus, what else is on the left side of this equation? Those gold +3's, right? So that would be AU +3, but we're going to include those back with the nitrate. So AU NO3 3, right? We are then going to turn that into 3 lithium nitrates. That's really the lithium ions that were here, but we're going to show them with their nitrate formula. And we are going to get AU 0. So that's sort of a throwback to what we did in the first section of this unit. All right, but we don't need to accommodate those coefficients when we're figuring out voltage. So if we use AE table D to figure out the voltage for the lithium half, we are going to get the lithium half, which is oxidation, so we're going to have to reverse the sign to make it +3.04. The gold +3 is going to be, as the reduction half, is going to be +1.50. Okay, so the total voltage for this altogether is going to add up to 4.54 volts. That's positive. Okay, so let's see if we can, I'm going to pause the video. My video time is going to run out at 15 minutes. So let's see if you can diagram this wet cell based on the diagram we did in on the last page. All right, so you're going to try to draw this wet cell. You're going to label the anode, the cathode, the positive and the negative electrode, the load, the salt bridge, the direction of the electron flow, the direction of the anion flow across the salt bridge, the direction of the cation flow across the salt bridge. Okay, see what you can do. You can pause the video right now and then come back and see if you can match up what I got as well. All right, compare your diagram to mine. Let me know if you have any questions. Try the next page, make your own combinations, and I will see you in the classroom.